Hello, everyone. I hope the sound is good. So today, Walker is going to tell us about quasi-categories and...
Simplicially enriched categories.
Oh, okay, simplicially enriched categories. Sorry, I'm not able to read.
Simplicial set categories.
Oh, I see.
Yeah.
Okay. Perfect. Okay, yeah, just take it away.
So before I begin, I want to say a couple of words about what this 4-lecture sequence is really going to be, because it fits into a sort of odd slot. Because of previous talks in this seminar, most people here already have some motivation for what homotopy coherence is, why we might care about higher categories. And similarly, I know from experience that if I wanted to cover all of this material completely rigorously with proofs, that's a semester-long course. So this is not going to be either of those things. The intent here is to go through some of the basic constructions in the theory of quasi-categories very specifically, and try to explain both how we can think about these things and how one works with higher categories in this framework. I should also say, because this fits into this sort of odd slot, feel free to, at any point, interrupt me. It's better to get through some material actually achieving the aims that I just laid out than to get through all of what I have planned not achieving them. So today I'm going to be talking about two models for infinity categories, quasi-categories and simplicially enriched categories. And so our basic object of study is the simplicial set. And I am aware that all of you are probably all familiar with this, but I just want to fix the notation that I'm going to be using going forward. So these are functors x from delta op to set, where this delta op has objects given by these standard linearly ordered sets and morphisms m to n weakly monotone. And this has some generating morphisms, which we can write as, say, delta I from n to n plus 1, which skips I, and sigma I from n to n minus 1, which doubles I. And so these data can be thought of as a functor or equivalently as some collection of sets, x0, x1, x2, with morphisms connecting them related to these generators. And I tend to follow a lot of the notational conventions in Jacob Lurie's work. So for me, the category of simplicial sets is written set sub delta, and this is the functor category from delta op to set. So let me also then briefly establish some notation for specific simplicial sets that are going to come up over and over again. So delta n is the simplicial set hom in delta from blank to n. And we can picture these as firstly a dot, then an arrow, then a 2-simplex, then a 3-simplex, and so on. So the k simplices here are maps, weakly monotone maps from k to n. By lambda ni, I will mean a specific simplicial subset of delta n. So these are what are called the ith horn in delta n. And which subset is this? This is the subset where lambda ni k consists of those f from k to n such that such that the image of f is not equal to n, and the image of f is not equal to n missing just I. So in 2 dimensions, we can draw all of these. So we have 3, lambda 2, 0, lambda 2, 1, and lambda 2, 2. Lambda 2, 0, well, we have 0, 1, 2, and we can't have the whole 2 simplex, and we can't have the edge that is given by skipping 0. Lambda 2, 1, similarly, we can't have the edge that is given by skipping 1, and lambda 2, 2, likewise. And then finally, we have boundary delta n subset delta n, which is the boundary of delta n. And this is given by requiring that the k-simplices are those f from k to n such that, let's see, the image of f is not equal to n. So the boundary of delta 2, actually, let me start with the boundary of delta 0. This is just the empty simplicial set. Boundary of delta 1 is 2 points. And the boundary of delta 2 is like the 2 simplex, but the middle is a hole. Okay, everyone okay with this so far? So our attempt to explain quasi-categories as a model for infinity categories will be based on a couple of principles. So both of these have appeared in previous seminars, but I just want to recall them briefly. So firstly, we have what's sometimes called the homotopy hypothesis. An infinity groupoid, that is an infinity category where all higher morphisms, including 1 morphisms, are invertible or weakly invertible, is the same thing as a cell complex and or topological space. So the idea here is you view the objects as points, the 1 isomorphisms as paths, the 2 isomorphisms as 2 cells, 3 isomorphisms as 3 cells, so on and so forth. And so the data to assemble an infinity groupoid will be the same data to assemble a cell complex. And then second, a statement which is perhaps a little bit obvious, but which will be important, at least in the way I intend to develop my definitions, is that every one category is an infinity category. And once again, this is a fairly reasonable thing for us to require. We would like our higher category theory to, in particular, subsume our one category theory. And as it turns out, simplicial sets a priori do subsume both topological spaces or cell complexes and categories. And they subsume both via a general construction called Uneda extensions. And the reason that I'm putting them into this particular framework, this is a one categorical concept, but the reason I'm putting them into this particular one categorical framework is because Uneda extensions are actually going to show up later. They're a very convenient way to relate the category of simplicial sets to something else. And so a Uneda extension proceeds by several steps. I'm going to write those down, and then I'm going to say what each of these are in each of these cases, spaces and categories. So the first thing we do is define a functor, and this is what I'll call a cosimplicial object Z that goes from delta to some category C. So the cosimplicial just means I'm not taking an op here. The second thing one does, let me actually move to the other board. Yes.
Are you assuming you know what the category is?
I am assuming that you have a vague nebulous intuition for what an infinity category should be. I am not assuming that you know any rigorous definition of an infinity category. So an infinity category should be a thing in which homotopy coherence lives. And from this idea, or from the idea that an infinity category should be a category that has one morphisms, two morphisms, so on and so forth, but all of the morphisms above dimension 1 are weakly invertible. From those two intuitions, one can extract that these two principles should be satisfied. Other questions?
The first two principles you wrote are just saying that spaces are a certain, should be a certain kind of category. Ordinary categories.
Yeah. No, thank you. Okay, so to construct a Uneda extension, we first define such a functor, a cosimplicial object. Then we take a left con extension along the Uneda embedding. So here we have the Uneda embedding, which I'm just going to denote by a capital script Y. This goes into simplicial sets. And we have our functor Z, and we get some functor left con extension along Y of Z, which in particular preserves colimits. And then finally, this yields an adjunction. So here we have, on the one hand, simplicial sets, and on the other hand, C. Here we have our left con extension along Y of Z, and here we have what I'm going to temporarily denote as n sub z, where n sub z of little c, the n simplices thereof, is just going to be given by the Hom set in C from z of n to c. Okay, so this is somewhat abstract. So let me now tell you how this manifests itself in topological spaces and categories.
You're assuming
Yes, I mean, there are a number of properties that you actually want here. Usually, actually, every time we're going to use Yoneda extensions in these 4 lectures, C is going to be complete and co-complete. And indeed, actually, in most of these cases, everything we'll be working with will carry some sort of model structure if you want to work with that much data. But yes, take C to be at very least co-complete so that the left con extension is given pointwise. So in topological spaces, what is this functor? Well, there is a fairly canonical way of getting a co-simplicial object in topological spaces. We're going to send the object n to what I'm going to write as the realization of delta n. Now, this is another place where my notation diverges a little bit from, say, classical homotopy theory notation. A lot of classical homotopy theorists would write this as just delta n, whereas I reserve that for the combinatorial n simplex that I'm going to be writing much more often. And this is just the set of elements in R n plus 1 greater than or equal to 0, such that the sum over I of the TIs is 1. So these really are just the geometric n simplices, and from this we get our nice co-simplicial object. Then when we take the left con extension, what we get is a functor from simplicial sets to topological spaces, which we call the geometric realization. And this sends a simplicial set X to the topological space, which is given by a disjoint union of xn cross these standard n simplices modulo an equivalence relation. So this is the usual geometric realization of a simplicial set. And here, the functor n realization is what's usually denoted by sing. This is the singular simplicial set functor. So that sing of a topological space Y, n is just going to be the set of continuous maps from this geometric n simplex into Y. And then in categories, well, this functor is just the inclusion. We can view every partially ordered set as a category, and we can view delta as just the full subcategory of categories on these partially ordered sets. So this simply becomes the inclusion. And here, taking this Yoneda extension, we get a functor that's a little bit tricky to describe. That's usually called tau1 or the fundamental category functor, but I'm not actually going to give it a name, which sends x to, yes, that is cat, which sends x to tau1 of x, where the objects are the zero simplices of x, and the morphisms are something like equivalence classes of simplicial paths. But here in this cat situation, the important part is really the corresponding nerve operation, n tau1, which I'm just going to call n, is the nerve. And this is given by nc has n simplices, given by precisely the set of functors from n to c. So these are hopefully quite familiar constructions, but they do both fit into this general framework where you just start with a cosimplicial object and then everything else follows. Yes.
So, what about the singular?
Yeah. Yeah.
So, if we define the concept
Yeah.
will we relate extension?
So the way that you get the singular chain complex is you pass through the singular simplicial set functor, take a free abelian group, and then take the Dold-Kahn correspondence. So the Dold-Kahn correspondence itself can also be viewed in this light. You have the normalized chains functor and the inverse of that.
Yeah, but what I'm wondering is,
If well, but then you don't have topological spaces involved in the mix. So
you assign a
yeah.
complex to every simplicial set.
Yeah. So
My
yeah.
question is then, we consider that functor from
You can, yes.
yeah, okay.
But in that case, it is much better to pass through Dold-Kahn because Dold-Kahn is a nice equivalence of categories. But yes.
Yeah.
Okay. Other questions before we move on? So that's because I didn't really tell you exactly what they are. So, no. So let's say we have a simplicial set that looks like this, and here we have x, and here we have y. Well, then a morphism in here from x to y could be this simplicial path, or it could be this simplicial path. But you have to consider both of those to be equivalent because there's this two simplex saying that basically the composite of this and this should be this. And so you're taking some sort of equivalence classes of simplicial paths from x to y. Again, the precise construction here is not going to come into play. The dual of the nerve construction, wait, big part? Yeah, so, yes. So this is the right adjoint of the nerve construction. And again, it's a little bit hard to describe explicitly because it's a quotient of some sort, a co-limit of categories. Yes, so if in the special case where x is a concomplex, which I'm going to define in just a moment, but in the special case where x is a concomplex, all tau gives you is the fundamental groupoid. So the fundamental groupoid can be constructed simplicially by taking, again, equivalence classes of simplicial paths, so long as you live in a concomplex. And so this tau1, this so-called fundamental category functor, just does the same thing, but now you're not really assuming that anything is invertible. No, it's not zigzags because you don't want to assume that things are invertible, right? A path has to be directed in this case. What you really end up wanting is that tau1 of n of c is actually isomorphic to c. So you don't want to take zigzags because that would in some sense forcibly invert your morphisms. And another way of seeing this is because of the way we defined the initial cosimplicial object, you're sending delta n to something that has non-invertible morphisms. Right? The initial cosimplicial object has to send delta n here to the category n, which is not any sort of groupoid. In the special case where this already behaves like a groupoid, where this is a concomplex, then you do get a groupoid here, the fundamental groupoid. Does that make more sense, or? So, yes, it is possible to give plenty of very explicit definitions here, starting from the co-limiting formula given by the left Kahn extension, but then building down to really say what the objects and morphisms are. I'm not really going to be using tau1 at all, which is why I don't particularly want to go through the full definition, but if you want, we can gladly talk about it afterwards. Yeah. So, the nice thing about both of these functors that we get, the nerve and then this realization thing adjunction, is that both of them are characterized by lifting properties. So let's let pi from x to y and I from a to b be morphisms in simplicial sets. We say pi has the right, sorry, let me write it out, right lifting property with respect to I, and I has the left lifting property with respect to pi if every commutative diagram where on the left-hand side we have I, on the right-hand side we have pi, and for the top and bottom we just have some morphisms, can be completed to the same diagram. Nope. And in this case, we say the square star admits a lift. So this is also a more classical homotopy theoretic notion, For instance, in topology, Serre fibrations are characterized precisely by lifting properties against the inclusions of, let's see, dn minus, dn cross 0 to dn cross I, where d is the disk. So we're going to characterize the simplicial sets that behave like spaces and the simplicial sets that behave like categories in terms of lifting properties. And the first of these characterizations is, again, hopefully somewhat familiar. It's what's sometimes called the nerve theorem. So this says the functor n from categories to simplicial sets is fully faithful a simplicial set X is isomorphic to the nerve of a category if and only if for every n greater than or equal to 2 and for every 0 less than I less than n, every lifting problem lambda ni delta n x has a unique lift. And in this case, we say X has unique inner horn fillers. So what do these combinatorial conditions mean? Well, those are specifying that this lambda has to be an inner horn. So, for example, we might have this lambda 2, 1, and in dimension 2, 1 is the only inner horn that we can have. And so if we have an inner horn in the nerve of a category, this means we have some f and g, and we want to extend this to a map from all of delta 2, but we know that that is unique because composites are unique in categories. So this tells us precisely how we understand categories as a special case of simplicial sets. Categories are the same thing as simplicial sets that satisfy this unique lifting condition. Yes?
And starts from
2, yes. I mean, technically, it's still correct if you put 0 there because this condition excludes any horns in the cases n equals 0 and 1, but you're right, it was a typo. That's entirely plausible. Yes. So n starts from 2 because this condition doesn't allow anything smaller. This is probably a different form than you've seen the nerve theorem in before, or maybe it is. The nerve theorem is usually expressed in terms of Siegel conditions or spine extensions. This is equivalent. The reason I haven't put a citation here is The original nerve theorem, the one in terms of Siegel conditions, first appears in the work of Grothendieck, but I don't actually know where this variant of it first appears. Well, but the Siegel condition approach is, in some sense, quite different than this lifting property approach. It might actually be Joyal's work on quasi-categories where this first appears explicitly in this form. Okay, so now on the other hand, we want to characterize the simplicial sets that behave like spaces. And for this, I'm going to write down a classical model categorical theorem, and then I'll explain how we should interpret it. It's okay if you don't really know what the model categorical theorem is saying. The important part is that there's a special class of simplicial sets that behave like topological spaces. Yeah.
This is just the lifting property.
It is actually equivalent to, yeah. So you can always stick the terminal object in the bottom right of the square, and you can always stick the initial object in the top left of the square. So these sorts of lifting and or extension properties, a special case of them is always going to be either just the upper triangle or just the lower triangle. Yeah.
Somehow related to the category of confidence in the category being Cartesian motive or something to have unity that corresponds to this form.
So
is there
so if you want Cartesian morphisms in this category, you actually need some extra data decorating this. Also, those correspond to not just inner horns, but outer horns and specific outer horns. So Cartesian and co-Cartesian correspond respectively to the case where you allow this or to the case where you allow this. And this is something that I will hopefully get around to talking about in 3 talks. So the last talk of this sequence will say a little bit about how we interpret Cartesian and co-Cartesian morphisms in this schema. Yes. How am I doing on time, by the way?
Good.
Good. Excellent. That's what I wanted to hear. Okay, good.
But I think we started 5 minutes.
Okay, yeah, then I still have some time, which is good. Okay, so a map pi from x to y of simplicial sets is called a confibration if it has the right lifting property against all horn inclusions. That is, 2x So before I complete the definition, let me briefly suggest one possible interpretation of this. The realization of lambda ni is always going to be homeomorphic to dn minus 1 times 0, and the realization of delta n is always going to be homeomorphic to dn minus 1 times the interval, and we can make a commutative diagram like this. So for those of you who are more comfortable with, say, the classical homotopy theory of topological spaces, you can think of this as sort of a combinatorial analog of the lifting conditions that define Serre fibrations. This is a big disk, and this is a hollowed out disk, if you like. And so we're just saying we can extend homotopies. So a simplicial set X is called a concomplex if the unique map from X to the terminal object is a confibration. We then say X admits horn fillers. So these concomplexes are going to be our good models for topological spaces. And the theorem which makes this apparent, I'm going to phrase in model categorical terms, and then I'm going to interpret it. Yes? That is completely incorrect. It is not at all unique. Thank you very much. I still had categories on the brain. No, many thanks, yes. The nerve of a groupoid is always a concomplex. The nerve of a category is not usually a concomplex. And this is good because we expect concomplexes to model infinity groupoids, right? One of our assumptions was that infinity groupoids and spaces are the same thing. So concomplexes should be infinity groupoids. That means that general categories shouldn't be examples of infinity groupoids, but groupoids should. And actually, showing that the nerve of a groupoid is a concomplex is not that difficult to do and is a nice exercise to sort of test one's understanding of the combinatorics underlying this framework. Yeah. There is a model structure on the category of simplicial sets such that f from x to y is a weak equivalence when the realization of f from the realization of x to the realization of y is a weak homotopy a cofibration when the individual components are injective for any n. So this is level-wise injective, and a fibration when it is a confibration. Moreover, the adjunction that we constructed, where this is the realization, and this is sing, is a Quillen equivalence. So let me briefly interpret this statement. What we mean when we say there is a model structure is basically there's a well-defined homotopy theory of these things, very well-behaved homotopy theory. You can use the classical machinery of cofibrant resolutions and fibrant replacements to work with homotopy in this category. And what this in particular means is just as every topological space can be equivalently replaced with a cofibrant topological space, that is, a retract of cell complexes, every simplicial set can be replaced equivalently with a fibrant simplicial space, that is, a concomplex. And so what this final statement is saying is that the homotopy theory of topological spaces is in fact equivalent to the homotopy theory of concomplexes. So the upshot, concomplexes are good models for spaces. This also implies, and this is something that using this observation and some elbow grease, one can actually work out oneself, that the singular simplicial set of any topological space will in fact be a concomplex. Yes? A Quillen equivalence is a Quillen adjunction that satisfies an additional property. So a Quillen adjunction says that this left adjoint sends cofibrations to cofibrations and trivial cofibrations to trivial cofibrations, and this right adjoint sends fibrations to fibrations and trivial fibrations to trivial fibrations. And then it being a Quillen equivalence means that the derived unit and derived co-unit are weak equivalences. A perhaps less arcane way of saying that same thing is that if you take the localization of these model categories, this induces an equivalence between those, an adjoint equivalence between those model categories. Yes, and actually I should also say this is jumping far ahead, but if you then say model categories present infinity categories via hammock localization, then Quillen equivalences will actually induce equivalences of infinity categories as well. So you have an infinity category of spaces here and an infinity category of spaces here, and those will actually be equivalent infinity categories because this is a Quillen equivalence. So it really is like the best possible notion of equivalence of homotopy theories, if you like.
When you try to prove it, as far as I remember, showing the existence of the model structure with the axiom for the difficult part, at least part of it.
Yes, well,
then prove that this is after you do that, is it?
So part of it is harder, part of it is easier. So in some sense, you're already sort of defining this to be a Quillen adjunction, right?
Yeah.
This type of cofibration will always be sent to an inclusion of cell complex as a cellular inclusion, which means that you're defining this to preserve cofibrations. And you're defining it to preserve weak equivalences. So it has to be a Quillen adjunction. Showing that the derived unit and derived co-unit are equivalences is non-trivial, as is showing the existence of the model structure. But showing the existence of the model structure is, I would say, the harder part. Yeah.
Both.
Yes, although this is also, if I remember correctly, this is Quillen's original monograph on model categories, where model categories were first defined. Yes?
What about showing non-existence of
That's harder. You have to show non-existence of a model structure with certain properties, and then you say, okay, if these properties existed, we would derive some contradiction. So you can show, for instance, that a certain model structure is the unique model structure on this category with X properties. And that's often done by showing that if there were another, it would either be equal or you would get a contradiction. For instance, the canonical model structure on the category of categories has this property. It's canonical in the sense that it's unique with the properties that you want it to have. Okay, other questions? Yeah.
So group model for spaces.
Yeah.
You said the spaces will be infinite groupoids.
Yes.
So complexes will be infinite groupoids.
Exactly, yes.
Infinite thing should have a extension, unique extension for complexes won't have.
No, an infinity category shouldn't have a unique extension. Yeah, right? Because you no longer have this sort of uniqueness of composition. You have uniqueness of composition up to some contractible choice because you can choose various two equivalences between your various possible composites. Yes, so groupoids, it will be unique. So a groupoid is a special type of concomplex where these horn fillers don't just exist, but they exist and are unique. And then it's a one groupoid on the nose. Much in the same way as the nerve theorem gave us categories on the nose. Yes, exactly. And that's what we're about to generalize. So yes, so we now know concomplexes are infinity groupoids, and simplicial sets with unique inner horn fillers are one categories. So what we're going to do to define quasi-categories is just take the minimal set of conditions that give us a nice generalization of both of these. So a morphism F from X to Y in simplicial sets is called an inner fibration. If it has the right lifting property against all inner horn inclusions. That is for n greater or equal to 0 less than I less than n. We can take any diagram of this form and get an extension. A simplicial set X is called a quasi-category if X to the point is an inner fibration. So what this definition is doing is it's basically saying, okay, categories are these things with unique inner horn fillers. Infinity groupoids have all of these extra fillers, these outer horn fillers as well, but none of them are necessarily unique. Let's define something like the intersection of these properties. We say a simplicial set is a quasi-category if you can fill inner horns non-uniquely. One way of thinking about this is you're giving up the idea that composition is unique, but instead you're requiring that it be unique up to some contractible choice. And that's something that we'll make more precise maybe next time. But for the time being, you could think of this as giving up the uniqueness of composition, but keeping the essential categoryness or category feeling of this simplicial set. So these are our quasi-categories. And it really does match our hopes in that every one category satisfies this condition and actually satisfies something stronger. Thank you. And every concomplex satisfies, in fact, something stronger than this. It has some additional horn fillers. So this is a generalization, but it is hard for us to say why this is the right notion of an infinity category. And so to hopefully try and justify that a little bit, we're going to come now after an hour to the second thing that I wanted to talk about. Namely, we're going to talk about simplicially enriched categories. And we're once again going to be leaning on this analogy pretty heavily. So the way we're going to be leaning on it now is we're going to be saying, well, if a concomplex is an infinity groupoid, then a category enriched in concomplexes should be an infinity one category. Much in the same way that if you enrich a one category in groupoids, you get a 2-1 category. So we now will say a simplicially enriched category is a category enriched in simplicial sets. That is, for every pair of objects, x and y, in, let's say, a category C, in the objects of C, we get a simplicial set, the mapping space in C. We write cat delta for the category of simplicially enriched categories. So I will say, again, I'm following mostly Lurie's notation. This is the notation from higher topos theory. I think that this notation is a little bit suboptimal because it suggests that what we're talking about is the category of simplicial objects in categories. This is, in fact, a subcategory of that. So by cat delta, I really do mean just the category of simplically enriched categories.
So we only need that the set of represents between x and y is a set.
I mean, you also need that the compositions are simplicial maps, and that associativity and unitality now hold as diagrams of simplicial sets. But yeah, it really is just a category enriched in simplicial sets. So if you write down the axioms of a category in terms of the mapping sets, and write them down as commutative diagrams rather than as conditions, say, instead of f of g of h is f of g of h for associativity, instead write the commutative square that represents that. And then you just say, okay, now instead of living in set, we live in our enriching category. What you get is the notion of an enriched category. Yeah.
Doesn't feel consistent with the set of the.
Yes, so I do not like this notation, but I'm trying to stay consistent with what I would say is now the primary reference for this theory, which is higher topos theory. And there, this is the notation used. I would usually want to write this as something like that. Yeah. Again, this is not simplicial objects in categories, even though the notation makes it really look like it should. Yeah. So I'm going to jump straight to the punchline here. So we have the following theorem of Bergner. There is a model structure on cat delta such that an f from C to D is a weak equivalence when f is essentially surjective and the induced maps C xy to D xy are weak equivalences of simplicial sets, and a category C is fibrant when C xy is a concomplex for all x and y objects of C. Moreover, this adjunction, oh, no, I haven't defined that adjunction yet. That's the next thing that I'm going to do. Okay, so, yes, moreover, the adjunction I haven't told you about yet is an equivalence. This is true, of course, but not very helpful. Okay. Yes, the cofibrations in this model structure are kind of awful to deal with. Basically, I'm giving the important pieces of information about this model structure, but this data does not completely characterize the model structure. Yes. Well, so if I had given you the weak equivalences and written down explicitly what the fibrations are, which is not actually that hard to do, that would uniquely characterize the model structure. If you take any model category, it is completely determined by either its set of cofibrations and its set of weak equivalences, or its set of fibrations and its set of weak equivalences. The fibrations are not terrible to write down here. I'm just writing only this because we won't really need the fibrations explicitly. The cofibrations in this model category are messy and best characterized as the things that have the left lifting property with respect to the trivial fibrations. That appears in a number of papers. I don't know where it started. So Bergner's paper, I think, is entitled a model for the homotopy theory of homotopy theories. But I think that phrase does predate. Yes. I mean, that's, I think, later than Bergner's paper. Anyway, so yes, that phrase permeates the literature. I don't know where it began. So, okay, so this model structure is more or less precisely what we want to say is a model for infinity categories. The fibrant objects are the things enriched in concomplexes, and the weak equivalences are the things that are essentially surjective and fully faithful up to equivalence. Almost precisely what we would like to be a model for infinity categories. So the last check to see that our notion of quasi-category is the right notion for us to work with is to relate it somehow to these simplically enriched categories. And once again, we're going to use more or less the same machine that we used before and turn the crank. So yes, you can define a model structure for quasi-categories. In some sense, this is one of the interesting things about developing infinity category from the ground up, is that you run into the issue of, once you've defined a model structure, how do you check that it is the right model structure, that it really models what you want it to model? Well, so in this case, what you say is, here we have two different things that we think should model infinity categories. If we can define model structures on both of them and compare them so they're equivalent, then we can be pretty confident that these should be what we want. Yes. I mean, showing that that's the right notion is a hard thing to really ask about, because it's not the sort of thing that you can prove, right? You can't write theorem, this is the right idea of infinity category. What you can say is, here are the reasons that I think that this is the right thing to work. Any more than you can say, topological spaces versus, what are they called? Condensed sets. Which is the right thing to work with? Well, that depends on your perspective, and this also sort of depends on your perspective. But what we can say very formally is that this captures one of our intuitions for what an infinity category should be. Complete Siegel spaces capture a different one, and quasi-categories capture yet another. And so these capture our various intuitions, and they're all the same. They're all equivalent. So think of this as motivation. Yes, sorry.
Perhaps so the classical definition of homotopy here was developed from this side.
Yes.
And lots of work was done on it. So now you need to show that that thing which was agreed upon, the homotopy coherence, you captured the quasi-category. That's what you're trying to do. But for working purposes, take that model.
Yeah. I mean, well, okay, so the working higher category theorist sometimes will have to use multiple of these models depending on what is convenient. And so that's another reason to really want multiple models and good comparisons between them. Okay, so for each n greater than or equal to 0, define a simplicially enriched category which I'll write as frac c of delta n with objects 0, 1 through n, and Hom spaces to be the nerve of the poset of chains. So this is poset of chains in N. And composition C delta n I j cross C delta n j k to C delta n I k sends C and D to different chains to C union D. So this gives a co-simplicial object and you can probably at this point see where I'm going with this, but first I do want to give an example just so that we understand what these things look like. Yes? So what I'm really defining here is a map of posets, and then you pass it through the nerve, and that gives you a map of simplicial sets. So the reason that I write it as this map of posets is because I don't want to write a chain of chains in any sort of notation. But yes, formally, here you have a simplex in here, which is a chain of chains and a chain of chains, and then you take the level-wise union to get this chain of chains. So, for example, the mapping space here is the square delta 1 cross delta 1. And more generally, your mapping spaces are going to look like cubes just because of the way that this has been set up. What does the composition look like? Well, this will be, let's take 0, 1. This is just a point, which is 0, 1. There's only one chain that's allowed by this definition. And this is an arrow, which is 1, 3 to 1, 2, 3. And it's not hard to see that taking the union, this is the image of that product. So this is, in some sense, closer to classically how homotopy coherence was defined. you define coherence by saying, okay, we have these posets of chains, and we now allow those to be sent to homotopies in a way that respects this poset structure. So what this is doing is defining a co-simplicial object that now treats delta n as a simplicial category. Yes, it should, because it always contains one. Thank you. It is that one. When I was writing my notes for this, I oriented the other way. Thank you very much. Yes. Okay, so Uneda extension yields an adjunction. And this is what's called the homotopy coherent nerve. And this is what, unfortunately, often in the literature goes by the name the left adjoint to the homotopy coherent nerve. But I tend to use the terminology rigidification, borrowed from Duggar and Spivak. Now, I'm not going to say much about computing this, but it is worth noting that there are actually a number of nice pieces of computational technology that allow you to say very explicitly what the rigidification of a given simplicial set is. The first of these is a paper by Duggar and Spivak, which characterizes rigidifications. But we actually have an expert somewhere here in the audience, Redi, who has also written somewhat extensively on how these can be computed. Yes? Then what you get is a thickening of that category, a homotopical thickening of that category.
We don't get anything, we get more stuff.
Yes, so you get coherence, basically. Like, delta n is the nerve of a category.
Yeah.
But what you get out of this has these big Hom spaces that have been thickened up to allow for homotopy coherence. However, on the other hand, you do have, so we have this nerve and this nerve. And we have here what I'll call n-Hom, where we just consider a category here as a category here by considering its Hom spaces to be discrete. Well, this diagram does commute up to isomorphism. But going the other way doesn't, because we want that to represent some sort of homotopical thickening of our category. Yeah. That also means that the associated diagram of left adjoints commutes, but that's, again, a different matter. Okay, so theorem, Joyal, thanks. The adjunction whoops, no. There is a model structure. I really just want to say that adjunction is an equivalence and be done with it, apparently. I keep on skipping fairly important steps on set delta such that the weak equivalences are those f from x to y such that if we apply this rigidification, we get an equivalence in the Bergner model structure the cofibrations are the level-wise injections. So same cofibrations as our model structure for concomplexes. And the fibrant objects are the quasi-categories. Moreover, this rigidification coherent nerve adjunction is a Quillen equivalence. So, oh, yes? I struggled a little bit with this. I will confess I didn't spend as much time tracking down references as perhaps I should have. The existence of the model structure is definitely due to Joyal. I think that this Quillen equivalence was known before Lurie, although Lurie gives a construction of this model structure that is substantially better suited to discussing this Quillen equivalence. But I do not actually know the first place this equivalence statement appears in the literature.
Do you know when Joyal stated this? Where the weak equivalence is defined like this by Joyal, or you're following Lurie?
So I am definitely following Lurie's convention here, but I think that this is also how they were defined by Joyal. It's actually somewhat tricky to characterize these so-called categorical equivalences of simplicial sets any other way. The fibrations and the weak equivalences are somewhat tricky to characterize on the simplicial set side. And hopefully in the fourth lecture, I'll explain how a slight adjustment of the combinatorial framework gives you a better handle on the weak equivalences, at least between fibrant objects.
What are the vibrations?
I have not told you, and that's because they're very, very hard to characterize in general. Between fibrant objects, the fibrations are those things which are something called an isofibration, which means that they have a certain lifting property with respect to the nerve of the walking isomorphism, and inner fibrations. But that's only true if both of the objects in question are fibrant. Between general objects, hard, basically. What are the fibrations? Hard. So the last thing that I want to say, and then I'll stop, is that this does allow us to start making more categorically flavored definitions in quasi-categories. So we can call the mapping space in a quasi-category X. So if we have a quasi-category and we have two zero simplices, so objects, we can call this our mapping space. And so this allows us to make some basic definitions. So for instance, then we can define, for example, x in x naught is initial if for every y in x naught, this mapping space is a weak equivalence. That is, if this space is contractible. Now, I mention this, even though I'm going to go more into detail on actual quasi-categorical constructions next time, because this illustrates an important feature of how one generalizes definitions from one categories to infinity categories. If you want to make a definition, say, of an initial object, you take the word unique, and then unique no longer really has any meaning in the infinity categorical context. So what you want to require instead is unique up to contractible choice. So we're no longer saying there's a unique morphism from x to y. We're saying there's a contractible set of morphisms from x to y. It doesn't have to be unique, but it has to be unique up to contractible choice. And then the last thing that I want to say is to raise a slight issue that we will deal with in the next two talks, namely the following problem. C x xy is not, in general, a concomplex, which makes it somewhat hard to do simplicial homotopy theory with it. So in the upcoming talks, we will discuss some solutions to this and also discuss how we start to build up a category theory in quasi-categories, how we can make categorical definitions in the setting where we're only working with quasi-categories, and the ways in which these generalize previous one-categorical definitions. Okay, I think I'm going to stop there. Thanks very much for your attention. And yeah, if there are any questions, feel free to ask.
Question.
Yes.
We used to draw this Venn diagram that you have two circles intersect, where the whole thing was in categories.
Yeah.
Quasi-categories.
Yeah.
One of them is nerves of categories.
Yes.
The other one is the complexes.
Yes.
The intersection is the nerve of the groupoids.
Yes. So just for nerves of groupoids, nerves of categories, concomplexes, quasi-categories. That Venn diagram.
My question is, so when we took the quasi-categories for the hybrid objects, we got this model category structure of 12. We took the complexes, we had this other model, like the usual one that gives you top.
Yes.
If we took the nerves of categories, do we get the model category structure on categories? Things like that is possible? So
there is a model category structure on simplicial sets. Is there? No, hold on. I don't actually know if there's a model category structure on simplicial sets whose fibrant objects are precisely the categories. That's a little bit tricky because the fibrant objects need to be characterized by a right lifting property in the general sense. And so you can't require this uniqueness of lifts. there might be a way around it, but I must confess it's not something that I've ever thought about. I mean, this is perhaps laziness on my part, but we do already have basically the best imaginable model for one categories, which is the canonical model structure on the category of categories. And then the nerve fundamental category adjunction is a Quillen adjunction, which means that that really does model the inclusion of the infinity category of categories into the infinity category of infinity categories.
For group weights,
Mm-hmm.
you can localize the controller model structure to give you group weights as vibrant objects. You make some cofibrations invertible, and I guess it's interesting, but something like that might. So if we localize the gel model structure to make some cofibrations invertible, I guess you would get vibrant objects category. We have to check.
Maybe, but like again, I think that it is possible, but I do not know the answer off the top of my head, and I wouldn't venture to claim one way or another whether there is such a one.
I'm gonna slightly bet in favor.
Fair enough. But again, somehow, in this case, it's enough to know which quasi-categories we can think of as one categories. And those are the ones where these inner horn fillers are unique. I mean, there are a bunch of other nice relations between these concepts. So if you have a quasi-category and you know that it's a fundamental category, so you hit it with this tau1 functor, if that gives you a groupoid, then it's already a Kahn complex. You only need to check the invertibility of one morphisms in some sense. You don't need to check all of these lifting properties. Other questions? Okay.
Okay, let's thank Walker again.